It's often the case for sample spaces of experiments that we actually care about in practical applications to have non-equally likely probability distributions. So we're going to take an example of one of those here by supposing that we're going to roll a pair of fair dice and then add the number of dots that are showing on each die and look at all the possible sums. Little correction on our handout here of 2 through 12, and we want to construct that probability distribution. Well, suppose we're going to roll the two dice. Each die can come up 1 through 6, and when you combine them then, the minimum sum would come with a pair of 1s, which would give a sum of 2, and the maximum sum would come from getting a 6 on each die, double sixes for a roll of 12. Now, as things are drawn right here, any one of these rolls, say a 5 on the first die, a 3 on the second, is exactly as likely as any other one in here, say a 3 on the first and a 6 on the second. You can see easily that there's 6 times 6 or 36 possibilities here, and so the probability of any one of these outcomes is 1 over 36, so that's equally likely. But that's actually not what we were asking for in our problem description. What we want is to add the number of dots that are showing on the die and then make a probability distribution for the sum of dots. Now, when we start looking at the sums, we can see that we are no longer looking at an equally likely situation anymore. For instance, to get a sum of 2, there's only one way, and that's the same for getting a sum of 12. But if we were to look along, say, this diagonal here, 6 and 1 add to 7, 5 and 2 add to 7, so do 4 and 3, 3 and 4, 2 and 5, and 1 and 6. So there's actually 6 ways of getting a sum of 7, and that makes a sum of 7 times more likely than a sum of 2 or a sum of 12. If we were to mark up our table, we could count all of these up. One way of the 36 to get a sum of 2, 2 ways out of the 36 to get a sum of 3, etc. The most likely is a sum of 7. There are 6 ways of doing that. And then we notice that there's really quite a bit of symmetry here. The 136 agrees for both the sum of 2 and 12. 236 for the sum of 3 and 11, etc., all the way through that table. So this is symmetric, but it's certainly not equally likely. So here is a non-equally likely sample space, really the first interesting one that we've encountered in the probabilities that we've been computing, and this is the probability distribution for the for this example here, starting off section 5. Now, we could do this for any number of setups that the physical situation produces outcomes that are equally likely, but we can combine them up in certain ways and get non-equally likely probability distributions. For instance, a family has 3 children in succession. We'll ignore the possibility of twins, and we want to say that both boys and girls are equally likely. Count up the number of girls they have. What's the probability distribution for the number of girls? Well, you see that for 3 girls, there's one way of doing that. For 2 girls, there's 2 ways. For 1 girl, there is likewise 3 ways. The girl could come first, second, or third, and then finally there could be no girls at all. So the probability distribution then would be this. The number of girls out of the 3 children could be 0, 1, 2, or 3. The probability would be, well, there's only one way out of these. There's a total of 8 here. 1/8 is the probability of 0 girls. Probability of 1 girl, there are 3 ways of that happening, so 3/8. Probability of 2 girls likewise is 3/8. And the probability of 3 girls is the same as the probability of no girls, 1/8 once again. So that is the probability distribution for the number of girls in 3 births. Now let's take a look at some of our previous distributions and go back and use them to compute some probabilities of compound events. So I want to go back right now to be thinking about the example of the sum of dots on a pair of dice. So there's our probability distribution. We'd like to ask the question, what is the probability that the sum will be equal to 3? Well, that is directly off from our distribution. You just look it up. A sum of 3 has a probability of 2 over 36, which of course would simplify to 1 over 18. What's the probability that the sum will be less than 3? Well, now this is a compound event. Less than 3, no, I guess it's not. That's 2 is the only possibility. That's 1 over 36. How about this one? What's the probability that the sum will be less than or equal to 4? Well, the sum less than or equal to 4 would be this one, and this one. That would give us a total of 3 plus 2 plus 1, 6 out of 36, or 1/6 is that probability. Notice that what we're doing in that case is simply adding up the probabilities of these separate outcomes that are included in our event. For the sum to be odd, that most likely is a half, but let's just check. In order to get the probability of an odd sum, we would take the probabilities of a sum of 3, 5, 7, 9, and 11. You add those up. 2, 4, 6, 9, and 11 divided by 36 does add up to 18 out of 36. So the probability that the sum is odd is 18 out of 36, or 1/2. How about the case with the number of girls in the family of 3 children? The probability of 2 or more boys, well, we could get that by looking at 2 or more boys, by the way, would be the same as the probability of 0 or 1 girls. So at most 1 girl. And we want to recast it that way because our distribution is in terms of the number of girls. At most 1 girl, here and here. 1/8 plus 3/8, 4/8 is 0.5 or 1/2. The probability of all girls, well, that'd be 3, 1/8. And the probability of an odd number of girls, 1 or 3, so 3/8 plus 1/8 is 5/8. Let's try that again. 3/8 plus 1/8 is 4/8, or 1/2 again. So that's how we can use these probability distributions once they've been constructed to answer a number of problems, and it does tend to make things move along quickly. The last thing we want to talk about in our introduction to probability is that people sometimes use the language of probability, but at other times they use the language of odds. Odds are particularly popular when talking about games of chance and gambling. So let's just set up a very simple situation. where we can quickly go back and forth between odds and probability. Probability and odds are not the same thing, but they are very closely related. If you have one, you can always switch to the other, and we'll show how you might be able to do that. Let's suppose that we had 5 marbles in a box. 3 of them are red, 2 of them are blue. So if it helps any, it sometimes helps me just to keep track of what I'm working with. I have a box here. I've got 3 reds and I've got 2 blues marbles, and the idea is you mix those up and you draw one out at random without looking at it, and ask the question, what are the odds in favor or the probability of getting some particular event. So let's say the event E is that the marble that is drawn is blue. Well, assuming these are well mixed and we're really drawing randomly, then the probability of selecting a blue marble is there's 2 out of the 5, 2/5 or 40%, is the probability of getting a blue one. Now the odds in favor can be computed this way. It's the number of ways to get the event. So there's 2 ways of getting a blue marble. Write a colon and then write the number of ways for the complement of the event. Well, if you don't get a blue one, you get a red one in this case. So there's 3 ways to do that. So we'd say the odds in favor of blue, that's what the event E is. The odds in favor of blue are 2 to 3, or sometimes people will write it out, 2 to 3. That is also an acceptable way to represent the odds, and confusingly, sometimes this is written as a fraction of 2/3. So personally, I don't like this very well. I would prefer to reserve the fraction form for probabilities just to kind of help me keep straight of what I'm working on, but it's not wrong. If someone says the odds in favor of blue is 2/3, that's actually correct. Now, the odds against an event are they're done in almost the same way as odds in favor. Here we do the number of ways, or you could say the probability of getting E compared to the probability of not getting E. You just switch these around to get the odds against E. So the number of ways of getting a blue, we're doing the odds against E. The number of ways to not get a blue, 3 ways. The number of ways to get a blue, 2 ways. So you could also say that's 3 to 2. Or you could say that it's 3/2. All of those are valid ways of representing the odds against blue. All right, so that's it. We now have an introduction to probability, and also talking about how you can translate from probabilities to odds, which is a common way of representing likelihoods in games of chance.